that your vector space Rn breaks down into two subspaces. I'll call them V1 and V2. And V2 is just the orthogonal complement to V1. So everything in this subspace V1 is orthogonal to everything in V2. Okay. So I'm going to let V1 have a basis. Okay. Let's do up to xk. So we'll assume it's a k-dimensional subspace. And let's assume that all of these vectors, we have an orthonormal basis. And then V2, which is V1 perp, the orthogonal complement, is a span of y1, y2, up to n minus k. That's how many vectors you're going to have in that subspace. Then, any vector u in Rn, as I've mentioned previously, has this unique decomposition. I'll break down to the u1, u2. So this belongs to v1, this belongs to v2. So if I define matrices whose columns are these basis vectors, so big X is x1 up to xk, and y is y1 up to yk, or yn minus k, then we can say the following, that u1 is just the orthogonal projection xx transpose applied to u, so that gives you that part. And then u2 would be the orthogonal projection onto this basis. But another way you can express it is just as the same as, since these vectors and these span the whole space, I could also say that this is equal to identity minus the x projection applied to u. So this gives you a way of separating a vector into, for instance, a component that's in the range and a component that's in the null space. So a lot of information I put out here that should at least contain sufficient breadcrumbs for you to find your way to the solution. Okay. I've never given this problem to Ken. Okay. I guess you should keep in mind that if a homework problem causes trouble at Stanford, it definitely won't go well here.
Probably true. I can see how you would come to that conclusion.
Probably should have figured it out beforehand. Okay. Now, since time is abundantly on our side,
Well, you could do it.
U1 equals XX transpose U.
yes. Okay. All right. Any other questions, whether it's about this problem or any other problem? Yes, Leah.
And I know we already talked about number one, but I spent like all day on it, and I don't know what I'm doing. So, am I trying to show that A is positive definite?
No, it is absolutely not positive definite.
No. So what am I trying to? I'm trying to show like for D, U, and L. I'm trying to express that. I'm trying to figure out how that relates from D to A, D, L, and U.
Yeah. Well, the problem with A is you don't know that it's symmetric. If it was symmetric, it actually would turn out to be positive definite. Just because of the relationship between A and B that you're given. But you do know that A and B have the same eigenvalues. The key here is, so if you're focusing on the iteration matrix, the m inverse n, that you get for SOR, for B, you have an LD in U for B, and you also have an LD in U for A. So the question is, how do those relate to one another? Because then, since you know that the iteration matrix for B has eigenvalues less than one absolute value, your goal is to show that the same thing is true for the iteration matrix for A. I don't know what manipulations you've tried up to this point, but you want to use a relationship between A and B to see how the various parts, the L, D, and U, relate for the two. And my sympathies for a miserable day you must have had spending all day on this problem.
Oh, this homework is awful.
More so than the other ones?
Yes.
Okay. Now, I should mention that there's a good opportunity to bring this up. So I mentioned earlier, for the fourth and final assignment, you have a choice. There's a programming project that's been up for all semester long, and earlier today I posted an alternative that has problems from demo related to eigenvalues. So, so just pick which one you want to do. So if you want to do more coding or not coding.
Is it posted under?
Assignments. Yes.
Maybe I would need to refresh.
Or probably.
Probably, yeah. No, probably not.
On the line 3,
Here?
x1, x2, xk,
Yes.
these are the eigenvalues of A, matrix A for not the one eigenvalue?
It does turn out that way, yes.
Yes?
Yes, yeah. I mean, I'm making a general statement here, but, well, actually, in terms of how you want to use it, and how you want to use this, this subspace would include a subset of the null space. This space here, all right. Well, the problem is if you choose any old B and you get non-convergence, then that means that B includes a vector in the eigenspace for where m inverse n is eigenvalue 1. And you need to get rid of that. You may not get rid of the entire subspace, but you don't need to.
For the example matrix,
Yeah.
that's right. The k equals n minus 1, right?
In this, yes, it does. Yeah, for that example.
For this example.
Yes.
B2 is a vector.
In part C, yes. Actually, for fixing this iteration in general, yes. Because in order to fix the iteration to make it work, you need to learn something about the null space. You don't need the whole null space, necessarily. Now, in part C, the null space is one-dimensional, so it's not very interesting. But but you just need to know enough about the null space to fix the problem. Okay. More questions on any other problem for that matter?
I guess since we've talked about everything else, we talked about number 2. So part B, number 2. So I think I have part A.
Okay.
But part B, it says, show that SSOR is equivalent to writing that system with that n and that n
Yeah.
from S equals m inverse n
Yeah.
as that. But I guess I'm confused because, like, this is what you normally start with, and then you have, I don't know.
Okay, because normally you have the M in the end,
Right, and then you're,
and now you're backing into it.
yeah,
And the reason for that is because of the SSOR is initially described as anything, it's not described in the usual way of a stationary method is because it's two stages.
okay. So are we just trying to find M and N?
Actually, you're not even trying to get
N, just
N,
M?
just M.
Okay, so that's all we have to do is find what M is,
Yes.
based on M inverse and
Yes.
N inverse.
Yes. And in a way, this part B kind of complements part A, because if you think of a typical stationary iteration, what I could do is write it this way. Okay, so that'd be M inverse NXK plus B. But what you're going to have is xk plus 1 is equal to some enormous mess. And in part A, you looked at, okay, what is the portion of this mess? What matrix is multiplying xk? So now, how are you going to get at M?
Right, I see.
Yeah.
Okay. I just didn't realize, well, I mean, I know it says find
Yeah.
M at the bottom, but I didn't realize that that's,
Okay.
that's all.
Okay.
I mean, I say that's all, but it'll still be. But now I understand what it's asking.
Okay, cool.
Yeah.
Well, that's half a battle. All right. Any other? Okay. So, let's try this is what I discussed earlier today. All right. Since we have a lot of class time left, for a number of questions, what I'm going to do is I'm going to continue with material. And there's a very good chance that I will finish everything by the time we get to the last day of class meeting, that is next Wednesday, which is the 29th. So if I don't cover anything, if I don't have anything left to cover, and we roll around to the 29th, we will just use that day as if anyone has questions about homework 4. So in effect, that class is optional then. So bring questions. We'll see what happens. I'll certainly know by next Monday how things are going coverage-wise, but because this last material, it is difficult. So, but in terms of pages of notes, it's not very much. Okay. But this is your last chance of any homework questions before I resume new stuff. Okay. What?
You just put that board up, so I didn't know if you wanted to switch, but it's cool.
I realized that I messed up the order, but I don't care.
Okay, cool. I don't have to move my iPad.
Okay. I'm happy to save you work. Save you work.
All I gotta do is stop it.
Okay.